Two galaxies 500 million light-years apart keep a shared rhythm. That rhythm was imprinted before the first stars formed. The immediate takeaway is this connection leaves measurable spacing in today's sky. Hidden connections are real patterns, not spooky telepathy. Gravity, light travel time, and ancient sounds set the links. We can trace those threads with hard numbers and maps. Picture a wide survey wall, sprinkled with millions of galaxies. Baryon acoustic oscillations are a fossil ripple pattern in galaxy spacing. They matter because they give the universe a built-in yardstick. In the early plasma, pressure waves raced outward from tiny overdensities. Photons pushed, gravity pulled, and the waves rang like drums. Recombination cooled the plasma, and the waves froze in place. That freeze left a preferred separation in later galaxy clustering. The scale is about 150 megaparsecs, or 490 million light-years. When we count galaxy pairs, that separation pops up slightly more often. It is a small bump, but it stands firm across surveys. Example in real terms, the Sloan map shows that bump very clearly. The signal is weak per pair, but strong across millions. We can then use that ruler to measure cosmic expansion. Distances become geometry problems, not guesswork or calibration ladders. Tiny test, imagine a grid where one cell equals the Bow scale. Now stack those cells from us to redshift 1 and beyond. The count translates into distance, then into the Hubble history. That yields constraints on dark energy and cosmic curvature too. One sentence recap, a sound wave yardstick quietly links faraway regions today. Bottom line, a Baby-Universe drumbeat still sets galaxy spacing now. A blue arc curves around a bright elliptical core, perfectly concentric. Gravitational lensing is light bent by mass along the line of sight. It matters because it lets the foreground weigh the background's secrets. A heavy galaxy cluster warps spacetime, and light follows curved geodesics. Multiple images appear, and paths take different times to arrive. Those time delays reveal distances and the clumpiness of intervening matter. The ring geometry also tells us the mass inside the arc. Here is a concrete case with numbers we can feel. A lens at 4 billion light-years can ring a quasar at 9. The arc radius might be a few arcseconds on the sky. Variations in the quasar's brightness repeat, offset by days to weeks. That offset gives a distance ladder, independent of standard candles. Meanwhile, weak lensing shears millions of faint galaxies in the background. That shear field maps dark matter across hundreds of square degrees. Rule of thumb, mass bends light, and light sketches the mass. So the picture is light from far regions threads around nearer gravity. Net result, distant galaxies and nearer clusters become one measured system. Wispy radio glow links two clusters like a torn cosmic bridge. Intergalactic magnetic fields are weak, pervasive fields threading the thin gas between galaxies. They matter because they steer particles and they sculpt where gas can cool. Galaxies eject magnetized plasma, and turbulence stretches fields along filaments. Cluster mergers amplify fields, and shocks light up long radio relics. Seed fields may trace back to early universe processes or first stars. We detect these fields through Faraday rotation of polarized background sources. The rotation angle grows with electron density, path length, and field strength. Numbers help. Typical intergalactic fields may be femtogauss to nanogauss strong. LOFAR has imaged bridges spanning tens of millions of light-years. Those bridges connect clusters in pairs, and sometimes along triple chains. Cosmic rays then follow these lines, reaching from node to node. Example, the Able 399 and 401 system shows a diffuse radio bridge. The separation is about 10 million light-years, lit by merger shocks. One sentence recap, weak fields still herd energy across enormous distances. Bottom line, magnetic scaffolding quietly ties distant environments into one network. A quasar flickers and a ghostly cloud lights up far away. A light echo is delayed illumination of gas by a variable source. It matters because timing translates into three-dimensional maps of intergalactic gas. The quasar brightens, photons race out, and distant clouds fluoresce later. The delay encodes distance, while the spectrum reveals temperature and composition. Hydrogen glows in Lyman-alpha, tracing filaments otherwise nearly invisible. We can watch the afterglow sweep across a cloud in sequence. Numbers ground this. The Slug Nebula spans about 2 million light-years. Its glow likely comes from a nearby quasar's powerful ultraviolet output. In other fields, echoes outline shells hundreds of thousands of light-years wide. Those shells mark bursts, and their light fronts race steadily outward. Rule of thumb, light draws a ruler wherever clocks can be compared. So the picture is quasar pulses sketched depth into the dark. Net result, distant regions share timing links through traveling illumination. A modeled sky of tiny warm and cool spots fills your view. The two-point correlation function measures how often temperatures match across angles. It matters because it tests the entire blueprint of structure formation. Quantum jitters stretched by inflation set the seeds before recombination. Sound waves then sculpted those seeds into a pattern of scales. We read that pattern as peaks and troughs across angular separations. The first peak sits near 1 degree, the sound horizon scale. Later peaks encode matter density and the cosmic baryon fraction. Example with numbers, Planck mapped millions of pixels with exquisite sensitivity. The spectrum's peak near multipole 200 reflects that 1 degree scale. Correlations beyond a few degrees drop, matching a nearly flat universe. Tiny test, cover the sky with coins 1 degree across. You will find similar spots recur at that spacing slightly more. That mild preference is the fossil handshake between distant regions. One sentence recap, skywide correlations carry early universe messages to us. Bottom line, the oldest light still links far patches through statistics. Filaments stretch like highways, and galaxies cruise along their lanes. Spin alignment is a weak tendency for galaxy axes to match filament directions. It matters because it checks how galaxies gain their angular momentum. Tidal torques from surrounding matter twist proto-galaxies as they form. Cold gas then streams along filaments, feeding disks and reinforcing spins. Mergers can flip directions, yet ensembles still show a small trend. Surveys compare galaxy shapes with local filament orientations across wide volumes. The signal is tiny per object, so samples must be huge. Numbers time, alignments of a few percent appear over tens of megaparsecs. One analysis used more than 100,000 galaxies to see it. The trend shifts with mass and with distance from nodes. Simulations predict these changes, matching the observed dependence fairly well. Example, disks often align with filaments, while massive halos tilt perpendicular. Rule of thumb, where matter flows, spins follow the flow's memory. So the picture is distant galaxies share inherited directions from shared rivers. Net result, the Webb's geometry imprints orientation links across space. Two black holes merge and space rings like a struck bell. A gravitational wave is a traveling ripple in spacetime from accelerating masses. It matters because ripples cross the cosmos, tying events to detectors here. Stellar mass mergers chirp quickly and ground detectors catch the short song. Supermassive pairs hum slowly, and galaxies across billions host them. Those slow waves stretch and squeeze pulsar timing like a metronome. Pulsar timing arrays compare many millisecond pulsars across our galaxy. Correlated timing wiggles reveal a common background, strongest at wide angles. Numbers help, years of data suggest a nanohertz gravitational wave background. Pairs at billions of light years probably dominate that deep hum. Meanwhile, individual lensed gravitational waves could arrive with hours of delay. That delay would connect a distant merger to multiple sky paths. Rule of thumb, synchronized clocks can hear ripples that eyes cannot see. So the picture is far regions broadcast through spacetime itself. Bottom line, cosmic rumbles knit the distant and the local together. Stand back with a calm gaze and trace one long thread. We chased a yardstick, bent light, faint fields, and traveling echoes. The loop closes here because one physics set links every scene. The takeaway is distant regions connect through gravity, timing, and ancient sound. If this untangled the web a little, consider joining for more. A gentle subscribe keeps these deep space stories flowing to you.